always try and anticipate a little bit what I'm going to be up against when you don't, who you're going to follow and who you're speaking. I'm hungry. I didn't anticipate that. I'm going to take a slightly different direction in a couple of ways on this, in that we're talking about reducing downtime, but I'm going to be talking about the safety aspect and what some of the safety systems and what they can do to downtime. The information you've gotten so far, really good information. The data collection, the use of that is very helpful and help us with analyzing some of the stuff we're doing here. But focus here on the safety aspect of it. One other thing is they'll see a little bit like, I feel a little bit like a rebel, because so far this week it's been a lot of DCS, continuous process control type stuff, which of course, being what this is, the information and stuff I'll use here is going to be way more towards the process automation controller type, discrete processes. Although that's really more of a case because I'm more comfortable in that and the information I can present. The theory behind it is really the same, whether you're in the continuous process control or the machine safety. The other thing is I think in continuous process control, you're more familiar with a lot of the safety aspects than what I'm running into with suppliers and stuff in terms of machine control. So a little background on 3M. We're a fairly big company, $30 billion a year company in sales. We got about 90,000 employees, operations in 70 countries, and sales in over 200 countries. About 6% of our sales are reinvested into R&D. And from a product standpoint, there's a lot of them. So I don't know if you picture us like a chemical company. We certainly do have the chemical wing. We do have a lot of the DCS, continuous process control type stuff, but we also have a lot of other type manufacturing that goes with it. I think these are some of the common ones. I think maybe the most interesting part of the whole thing is just the statement up there. They like to advertise you're rarely more than 10 feet from a 3M product. And in fact, if you got a cell phone in your pocket, you're a lot closer than that. The safety aspect of it, again, I think this is pretty well understood on the process control end of things, but maybe a lesser degree on machine safety control. Just because of the time, I don't want to spend too much time on this, but I wanted to put it in the slides. I think ARC will make the slides available to people, so if you want to come back and see where I'm getting some of this, you can do that. But I'm going to try and go through this, what people sometimes call kind of the boring stuff, kind of fast if I can. But basically, we're faced in the US with the general duty clause, which is essentially federal law that says that you can't hurt anybody. As soon as you've hurt somebody, you've broken the law. It's pretty much that simple. What they do to determine how egregiously you've broken the law is compare you to the consensus standards that are out there and try and determine, were you doing everything that everybody else is doing? Were you coming up short? Are you doing more? And that all plays right into how OSHA cites violations from all the way from the de minimis down to the willful. It's a key component as to how that plays out, and you really want to avoid the red. Here's one slide that does talk about continuous process control. When you look at the standards that are out there, if you're familiar with that, you're probably pretty familiar with this, the ANSI ISA 840001, all your SIF, SIL type stuff that you do for those type processes. The international standards, essentially the same thing. But on the machine safety end of things is where I find sometimes a little less, fewer people informed, I guess, on some of the things we're doing here. But for machine safety, ANSI B11 series are the ones with the big driver on what we do in terms of machine safety. And in that regard, one of the things it talks about is risk assessment. So kind of like, again, on the continuous process side, we're probably used to the you're doing your PHAs and your LOPAS and those types of analyses to determine what you're doing. We're really doing the same thing on machine safety with risk assessment. This is just one example of a standard. This actually comes from a technical report, but it's really new. So I wanted to use this one because it'll probably go this direction. But they all look somewhat the same. So when you're doing the risk assessment on the hazards on the machine, you can see how easily it gets fairly complex fairly fast. Almost every machine I've ever worked with has some potential serious hazards. It's very easy for a machine to break arms, pull off limbs, even kill somebody. So you'll end up down there in the serious. And even if the exposure is low, you'll see the results. They're going to point you to needing that your risk level is high and point you to having to have a high level of function in your safety systems. So What does that mean? These days, in this particular chart, points you to category 3 functionality, PL level, performance level D, if you're familiar with that. You're starting to get into fairly complex safety systems already in terms of redundancy, diversity, and the types of things that you're doing there. A couple of things I want to standards before I get off of this is that within B1119, which talks about safety for machines, there's a couple of interesting sections in there you might want to look at. The forward talks about, a lot of people are used to with ANSI B11, everything needs to be control reliable. Well, actually in the forward, they acknowledge that through risk assessment, you can do things that are less than control reliable as long as you justify you're getting to tolerable risk through some other means. So that's an alternative to control reliability when it's appropriate. The other thing is that section 6.1 talks about, they acknowledge that the ISO standards, the category 3, category 4, PLD, PLE, and they're all ORs, are, for the purposes of the standard, acknowledged to be the same as control reliable. So it's the closest thing we have to harmonization between Europe and US, which helps me a lot because I have to kind of answer globally for these things. And my life would be a lot simpler if we did everything the same, or we can justify doing everything the same everywhere. And that kind of allows us to do that. The last thing is an NFPA standard for industrial machinery. I just want to point out this statement. It's in there a few times. This is the key one. But basically it's saying for safety-related functions, software and firmware-based controllers that are used in safety-related functions have to be rated for that type of duty. So you can't go using standard PLCs, standard systems to do your safety control, or standard drives. That's what it's saying there. You can't wire your safety-related controls through standard PLC, standard drives. Thus, your options are basically down to hardwiring your safety systems or using safety-rated PLCs, safety-rated drives, and things like that, if you want to stay in compliance with the standards. So here's an example of, I think this is a category 3 circuit. You can see where the wiring and stuff can, because you got redundancy and diversity and all these other things going on in there, the circuits can get pretty complicated pretty fast, and it's a lot of wiring if you're going to do it in a hardwired approach. From a diagnostic ends of things, what you get for diagnostics generally are LEDs. So you get the 3 blinking LEDs, a rapid blinking left one with a slow blinking right means something different than if they're all on solid red or yellow, and you got to look the thing up in the manual and try and figure out why it's unhappy. And the other thing that happens from that is if you're going to go the hardwired route, this is a slide that I use a lot at work, is the slide on the picture on the left there is from a panel from the 1970s when we were doing hardwired control of machines and relay panels. And the other one's quite a bit newer from 2010 where they chose, they're in compliance with their safety systems, but they're hardwiring them through safety relays. And you can see there's some ugly similarities there in the amount of time it takes to design and to wire and to check this stuff out, and then the long-term effect of having to troubleshoot this sort of thing. So what's the option to that? It's the safety PLCs. There are a number of advantages. Now, this is a little bit weird to call this downtime, but I'm doing it anyway here, is that it does reduce our design time phase and our checkout time. We can get through those faster, meaning this is really before the machine's put into production, but it's sort of downtime leading up to the machine going into production. You want that cycle generally to be as short as possible too, so that your pursuit of being first to market or getting capacities up or whatever you're doing. And so it's certainly beneficial to that. Then the remaining ones, have more to do with the life cycle of the machine. So like, again, simplified field wiring, basically you can find your problems faster when there is a problem. And then programmable safety, this is a big part of it. You got smarter safety logic, so it's a lot easier to program how the machine behaves based on the status of what the machine is in. If I want to get into this machine section and it's in such a state that I should be allowed to go in because there's nothing dangerous going on there, the rest of the process might be able to keep running and allow me to do that. Now you can do that with hardwired controls too, but you end up with relays in parallel with relays and it can get pretty messy. The other thing is that we tend to run our machines 30 years or more, and products change, the demand, what the machine needs to be changes, so we'll redesign the machines, make modifications here and there. Well, it's sort of obnoxious to be in there and redoing your wiring on your safety systems as well, so it's nice if you can reconfigure a machine and just go in and programmatically reconfigure the safety systems too. And then the reduced downtime related to faster troubleshooting, which you can kind of see some of that coming up. The last one on this is the accident avoidance. This one's a little hard to quantify, but it might be the biggest player of them all, is the potentially large human and financial cost savings there if you have an incident. It's a little hard to know what that would be because it's stuff that didn't happen because you did this, so hard to predict what would have happened otherwise, but certainly a big player in why we do it. So that's the ultimate goal, is trying to keep anybody from getting hurt. There are a couple disadvantages. First one is the IT security concerns. This is not new, and so I'm not going to go into this much, but you know, so this conference dealing with security, it's really the same thing. So not to belittle the importance, it is important, but I'm not going to address that here. It's just as important here as everywhere else where we're talking about for your process safety. If people can get to your PLCs, they can change your safeties. I could go in from that computer sitting right there, I can log into the machines that I have access to, and I could program to be the opposite of safe if I wanted to. So you do have to pay attention to that. Higher initial cost tends to be more of the conversation piece. Safety PLC, safety IO, safety drives, they all do cost more than standard PLCs, standard IO, standard drives. Just like Dan, I also have a red and blue graph. Mine's not as fancy as his. This is data that I put together, but just doing some ballpark numbers I've done for the department in the past, trying to determine where these breakpoints are, where we want to go from a hardwired system to consider using a safety PLC. The red line's the hardwired stuff. It's pretty linear. Every time you have a safety loop, which is what I got coming across the bottom, you have to put in a relay, you have to do some wiring. That's a little bit of a simplification. Some loops are more complex than others. So really it's more dependent on the cost on the y-axis than coming across. But what it amounts to is the more there is, the cost linearly grows. The safety PLC, there's some investment cost initially, and then it's a flatter line. But it's got that weird step. And the reason is because on smaller machines, we can get away with what I would call like OEM type controllers. The smaller, more limited capability type safety rated controllers have limited expansion, some limited capabilities, but it might be suitable for this. Once we start getting out to machines that are big enough that we're seeing, you know, 16 loops, safety type loops or complex safety controls, then it justifies, well, or we start to stretch the capability of the processor, we go to the top of the line processor. And there's a bigger investment in doing that. Everything about that costs a little bit more. So that's why you see the blue line jump. But then once again, after that's flat. So, but by the time we get up to around $13,000, and this is $13,000 spent on just safety stuff, not the machine, but just the safety portion you're doing on the machine, it tends to be cheaper for us to go to a safety PLC type arrangement. And this is just initial capital equipment cost, which drives a lot of our projects because of the way we finance our projects and the way we do them. But it's not taking into account any of the things that we were talking about here in terms of improving our downtime and stuff like that. Those long-term benefits actually slide our decision to the left. And what we're finding at 3M is we're using safety controllers on almost everything but the smallest of machines now. So what's the simplification in field wiring? Instead of what you saw in that other slide with all the stuff that was all wired together and everything, it's essentially all inputs and outputs or networked. And on top of that, things like whether it's e-stop buttons or guard switches or light curtains or whatever, you're just wiring straight into an input or coming straight from an output. It's not an auxiliary contact either. It is the safety contact that's shutting you down or telling you should be shutting down. So there's no potential for error between the status indications and the actual safety contacts themselves. And then, like I said, network devices, you wouldn't even have this much wiring. If you got safety over network on your drives, you're already networked to your drive because you got to tell it how fast they're on. So it eliminates the wiring entirely. The programming environment looks the same as what we're used to. Whatever your programming environment you're used to, the safety environment probably looks very much the same. There is the addition of some canned safety instructions that assist in some of the things you do, but they're not hard to implement, although the safety logic can get pretty complicated. So one of the other things that we've done is we have, 3M utilizes a lot of standard code for regular process control, but we're also doing that for safety code now. So if we have a newer engineer, so they don't miss anything. They can pull the safety code out of the library. If they don't get it configured correctly, it won't work. So it's a bit of a way of kind of getting some consistency in how we do things. That in and of itself improves downtime too, in that maintenance starts to see the same logic all the time when they are trying to diagnose what's going on. You still see a lot of ladder logic in our safety stuff. Now I know a lot of people, it's not the most elegant language. I have, my uncle was a professor at Michigan Tech in controls, hates ladder logic. But when it comes down to a maintenance guy at 3 in the morning trying to figure out why something does, and it's a simple interlock, it's hard to beat ladder as far as, why isn't it on? There it is. Doesn't get a lot easier than that. And because all this information resides in the PLC, it's all available to whatever you're using for an HMI. So whatever you feel you want to do there in terms of status and faults and indication, control of resets, groups, group resets, reconfiguration, maybe the machine reconfigures. We have some of that, especially in our laboratory machines, where they may reconfigure the machine. We need to reconfigure the safety at the same time. You can tie that together and indicate what's going on. Maybe you have sequential type safety systems as they're going through their sequence of startup. Yeah, there's a lot of holes in this from the 3M auditor. I have to get through a approval process to get the slides out here to the general public. So if you're wondering where all the smears are, those aren't actually belong on the screen. But as you're trying to get through the sequence of stuff that you're doing, you can see exactly where you're at, and it's coming directly out of the safety logic. And then animating the alarms themselves. There's a lot of different ways that you may choose to do this, but basically every HMI these days gives you some means of doing some type of alarm display as well, where you get a message. So, we have a few different systems. We have some on our bigger machines where we have a dedicated system that runs on a PC for doing just this particular function. But some things I kind of want to point out on these that I found useful is that the timestamp and the message is pretty typical information. I think it's also useful if you have multiple PLCs, multiple controllers on the machine, you identify what controller is the source of that issue and the actual tag name, which doesn't mean anything to the operator, but it's really easy for the maintenance guy because he doesn't even read the message. He doesn't have to. He's just going to search for that tag. When he gets that tag, he's going to be able to figure out why it's not on or why it is on. It's not supposed to be on. The other thing he found is that on these types of messaging systems, operators don't recognize maintenance descriptions. And that sometimes confuses them because they see the message and they don't know if they're supposed to respond to that or not, if they miss something in their training. So we'll just put that on there too. If they see the maintenance and the response, they just call maintenance. Makes it a little bit easier getting the guy there a little bit quicker. And I think the other part for making these systems effective at getting systems back up and running quick is getting down to the actual source of the problem and not filling the screen with a lot of data. Dan led the perfect example, because I was going to mention it, one of my pet peeves when I get out of a machine is e-stop. Is you get machines where if you have an e-stop condition, every time there's an e-stop, they animate an alarm for every e-stop device on the machine. So when there's an e-stop, you get 60 messages because 60 things are e-stopped. The guy that just bumped the e-stop button with his hip knows that they had an e-stop. I don't even generate a message for e-stop. What I will do is I'll generate a message for e-stop when they try and reset. If they go and press the button, like I just did by accident, then he'll come up and tell them why they can't get the reset and something like that. Now, if you're also using this as a logging system, you may want to log a message, that you had an e-stop at such and such a time. But if you got a data collection system doing that, you don't need to use this for logging events. It's probably about all what I want to say there. And this, of course, this display, like the note at the bottom there, this is not only just safety messages, but your safety system can animate just like the rest of the process control does on there. Oh, and getting to that source, that's not an easy thing to do. That trying to get thing down to so it only displays the source alarm sounds like an easy thing, but it actually takes a fair amount of work. And one of the other things that I've learned is when we come up on a new machine and we have a system like this, I won't let the operator see it. I'll tape over all of the screens that are out on the line and just have one on my desk. Because when you first power up the machine, you might get the thing filled up with a lot of nuisance type alarms, and it may take you a couple of days to work those down to really what you wanted coming up. And the operators will learn in 2 days that that's a junk system. And it's really hard to say, no, we're just debugging it, and it'll be really reliable, and you'll find it useful in the future. So I don't even let them see it anymore until I get it to a level of satisfaction I think they'll be okay with. And then, yeah, the machine cases. When we provide some information related to what we see on our machines, a little tricky to do, but I was able to come up with 3. Again, I had to kind of genericize it, but they are actual machines at 3. On the first machine there came from an acquisition, and it lacked all of the stuff I was talking about ahead of this. Not only on the safety end of things, but even on just the regular process control end. And they had about 60% uptime and 60% yield for 36% utilization, and they thought that was when things were working about right. We built 3M Engineering, we have a central engineering group. We built a machine very similar in size, scope, process-wise to that machine. And a lot of different results. It has basically all the things that I'm talking about in here, not only for safety, so you can't blame all this on safety, but it had the safety and the process end of it. And it comes up on 98% runtime and 96% yield in that first quarter of operation. Engineering hasn't even left the site yet, and they're hitting those kind of numbers. Of that 2% downtime, 0 was getting equated to the safety systems being responsible for it. Wanted to make a comparison to a hardwired system. It was very hard to do in magnitude. So the third example I was able to find does provide that, but it's about a 20% of the size of the machine of the previous example in terms of just the number of safety functions that are going on there. Because if it was any bigger than that, we'd be using the safety PLC and we wouldn't be hardwiring it. But this is a machine happens to have about 92% uptime, 6% of that 8% downtime is due to product changeover. So the remaining 2%, they see a month over month, typically about 0.25% related to safety systems that are logged by maintenance or logged by the system actually, that they're trying to pursue in the hardware system, trying to figure out why it stopped them or why it won't let them start. And to this day, I hear from them about that they wish they had gone the safety PLC when we were first talking about it, but they didn't want to spend the money when that one went in. It was kind of right on the borderline it was going to cost less hardwired, but they're seeing the long lifetime effects of it now. And I think that's everything I got. My question slide's still there, but okay, thanks.